Welcome back, everyone. Today we're diving into an absolutely crucial part of our software engineering journey. So, in previous sessions, we explored what a system actually does by looking at context models, and we figured out how things communicate using interaction models. But today we need to look at the system's actual blueprint. So, for this explainer, we're focusing squarely on section 5.3 of your textbook, structural models. Think of this as laying the foundation before we even think about laying a single brick of code. Here's our agenda for today's masterclass. First, an introduction to structural models. Second, understanding class diagrams. Third, managing complexity through generalization. Fourth, whole and parts, also known as aggregation. And finally, number 5, a quick final exam summary. All right, let's just dive right in. Section 1, Introduction to Structural Models. Now, when we talk about structural models, we're generally talking about two different perspectives. On the left side here, we have static models. This is literally how the system is organized and designed on paper. It's the static structure of the object classes. On the right side, though, we have dynamic models, which show how the system behaves when it's actually executing and running. And trust me, these are not the same thing. A system's dynamic organization of executing threads can look vastly different from its static component design. But for today's lecture, we're focusing entirely on that static modeling.
Moving on to Section 2, Understanding Class Diagrams.
Okay, golden rule of software engineering. Whenever we learn a new technical term, we define it first. So what exactly is an object class? Loosely speaking, an object class is a general definition or a blueprint for one specific kind of system object. When we're doing early requirements or software design, these objects represent something in the real world. Think of a patient, a prescription, or a doctor in a healthcare system. They aren't specific flesh and blood people just yet. They're the blueprint for those people in our system.
Now, in the Unified Modeling Language, or UML, we represent an object class using a simple rectangle, but we divide it into 3 distinct parts. I really want you to memorize this anatomy for your assignments. So, the top section holds the name of the object class, like patient. The middle section holds the attributes, or the characteristics of that object. So, for example, the patient's address. And finally, the bottom section contains the operations or methods associated with the class, like a function to change address when the patient happens to move.
But, as we know, objects don't just exist in total isolation, they interact. And this brings us to associations and multiplicity. An association is simply a link between classes indicating that a relationship actually exists. Because they're linked, each class has some knowledge of its associated class. Multiplicity, on the other hand, is a crucial little detail we add to that link. It shows exactly how many objects are involved in that specific association.
To really picture this, let's look at the MentCare system from your textbook. Notice the patient class linked to a patient record class. See the number 1 at both ends of that line? That's a one-to-one multiplicity. One patient has exactly one record. Simple enough, right? But now look below that, at the link between patient and consultation. On the patient side, it says 1, but over on the consultation side, it says 1 ... asterisk. That asterisk means many. So this is a one-to-many relationship. One patient can attend many consultations over time. Grasping this concept is absolutely fundamental to drawing accurate structural models. All right, let's wrap up basic class diagrams and jump into Section 3, Managing Complexity, Generalization.
So, how do we handle massive complex systems? We do this through a concept called generalization. Generalization is actually an everyday technique we all use to manage complexity in real life. Instead of learning the detailed, intricate characteristics of every single thing we experience, we classify things. We keep the common information in one place. In software, and particularly in object-oriented languages like Java, we implement this concept using class inheritance.
To really wrap our heads around this, let's look at an everyday example. Think about how we classify animals. Squirrels and rats are both members of the general class rodents. Because of this, they share common rodent traits. So a general statement, like all rodents have teeth for gnawing, applies to every single member of the class. By classifying them this way, we get to reuse our knowledge. We don't have to relearn that a squirrel has gnawing teeth, we just inherit that knowledge from the rodent class. Then we only have to focus on the specific differences between a squirrel and a rat.
So the crucial point is how we actually model this in software. Looking at the UML diagram from the textbook, the superclass is right at the top, doctor. Below it, we have subclasses like hospital doctor and general practitioner. Notice the UML notation here. It's an arrowhead pointing up to the more general superclass. That superclass holds the common attributes: For example, all doctors have a name and a phone number. The subclasses inherit those common traits, but add their own highly specific ones. A general practitioner works independently, so they might add a practice address, while a hospital doctor might add a staff number and a pager number.
Here's a quick lecture tip for you. Using generalization is a hallmark of good design practice, and it saves a massive amount of time. Imagine the national format for a phone number suddenly changes. If you didn't use generalization, you'd have to hunt down every single type of doctor class in your entire system and update the code manually. But with generalization, you only update the phone number format once in the general doctor superclass, and all the subclasses just inherit the fix automatically. It's a real game changer.
Okay, moving right along to Section 4, Whole and Parts, Aggregation.
This brings us to aggregation. Aggregation is a special, specific type of association. It simply means that one object, the whole, is composed of or made up of other objects, the parts.
Let's look at how we document aggregation in practice. In UML, we define aggregation by adding a diamond shape to the link, specifically right next to the class that represents the whole. Think about the textbook's patient record example. The patient record is the whole. What's it made of? Well, it's an aggregate of exactly one patient part and an indefinite number of consultation parts. The record holds the personal patient info plus all of their individual consultation notes.
Okay, everyone pay close attention because this is a massive exam focus. Students constantly mix these two concepts up. Here is the trick to literally never getting it wrong. Generalization is an is-a relationship. A general practitioner is a doctor. You represent this with a UML arrow pointing up. Aggregation, on the other hand, is a has-a relationship. A patient record has a consultation inside it. You represent this with a UML diamond next to the whole. So arrow means is-a, diamond means has-a. Seriously, write that down.
And finally, Section 5, Final Exam Summary.
If you want to absolutely ace the structural model section, make sure you can confidently draw a three-part class rectangle from memory, knowing exactly where the name, attributes, and operations go. You absolutely must know your multiplicities, specifically the difference between a one-to-one and a one-to-many relationship. Remember our exam focus. Generalization is the arrow. Aggregation is the diamond. And lastly, for this particular course, remember we're using South African English spellings in our assignments. So that's modeling with a double L, organization with an S, and generalization with an S.
To conclude today's lecture, why do we do all this drawing and modeling in the first place? Because structural models give us the static, architectural blueprint needed to start writing actual object-oriented code. You can't build a stable skyscraper without an architectural blueprint, and you sure can't build a reliable software system without a structural model. It's the bridge between understanding what the system should do and actually typing out the logic. But ask yourself this: if a structural model is just our static, unmoving foundation, what happens when the system actually turns on and the environment starts rapidly changing around it? Ponder that, and I'll see you in the next lecture where we explore behavioral models. Thanks for tuning in.